Today on this bonus episode of the Perception in Action podcast. What is motor noise? How does it shape how we learn new skills? So it's time for a call to action. Hi everyone, this is Rob Gray from Arizona State University and PerceptionAction.com. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. On this episode, I want to look at the role of motor noise in shaping motor learning by diving into a really interesting study from 2017. But first, what exactly do we mean by the term noise when we're talking about perceptual motor control? To understand this, I want to use an example from a paper by Van Beers published in 2009. Link in the show notes. Imagine you're playing darts and are trying to hit the bullseye. Your first throw hits the board 10 centimeters to the right of the bullseye. What should you do differently on your next throw? Should you aim 10 centimeters left of the bullseye to completely correct for the error on the last throw? Or if you want to hit the bullseye, should you just directly aim for it again? Or perhaps the best strategy is to do something in between, in this case aiming 5 centimeters to the left of the bullseye to partially correct for the error on the last trial. On the surface, it's not obvious which of these strategies is best. This is because we don't know what the primary source of the error was on our last throw. There are actually a few different possible sources, but for the purpose of today, let's consider just two. Throwing a dart involves our brain issuing a motor command in the form of a time-varying set of signals to our muscles. If we make an error in performance, it means that the command that was sent was inappropriate in some way. One possibility is that there was a problem with the central planning of movement. That is, the generation of motor commands in the premotor and motor areas of our brain resulted in a systematic error in the transformation from the intended target location into a motor command. In this case, the endpoint is systematically biased and does not coincide with the target location. This type of error is expected to be large for inexperienced performers due to the complicated mechanics of the arm and the multiple degrees of freedom involved. For example, a novice may not have learned that if they start the throw with their arm above their head, the consequent movement of the elbow joint will always cause the dart to go lower than planned. So the issue here is learning to control the multiple degrees of freedom in the system so that the intended outcome matched the planned one. Note that correcting this source of error could either come from a better motor plan or by allowing degrees of freedom to compensate for each other online. More on that shortly. The second way in which the motor plan could be inappropriate for achieving our goal is due to the presence of stochastic noise in the central movement planning and in peripheral movement execution. That is, noise in the relay of motor commands by the motor neurons and in the conversion into mechanical forces in the muscles. These will cause the actual motor output to differ from the intended output. In any biomechanical system, there are going to be random sources of variability. Neurons don't always fire at the same time, muscle contractions are slightly different. These sources of variability are unrelated to the strategy used by the performer or their level of experience. They are just inherent to the system. The result of this noise is that the actual endpoint will differ from the endpoint if no noise had been added. The presence of motor noise complicates error correction because it makes it impossible to know what the aim point of the previous movement was. There are an infinite number of combinations of planning inaccuracy and the effect of motor noise that could have produced a particular error. The error could be entirely due to motor noise, entirely due to movement planning, or a combination of both. In the first case, no correction should be made. In the second case, a large correction would be required, whereas a smaller correction would be necessary in the third case. So we need some way to neutralize this motor noise when learning a skill so that we can focus on correcting the error in our movement solution. How might we do this? The first way is something I talked about a few times now, developing motor synergies. If we allow degrees of freedom to compensate for each other in a perceptual motor system, it can go a long way to dealing with noise. For example, if the motor noise causes our shoulder angle to be slightly larger on a throw than usual, we can compensate for this by altering the elbow or wrist angle down the line in the kinetic chain. So in other words, we can deal with motor noise by developing an adaptable and flexible set of movement solutions. But there may also be an easier thing we could be doing. Avoid using motor solutions that have large amounts of noise associated with them in the first place. Due to individual differences in things like strength and flexibility, different movement solutions and body postures are going to be associated with different amounts of motor noise. A simple example is that it's difficult to keep your arm stable when holding it bent over your head at an unusual angle. It is also to be expected that stronger forces will lead to more noise. So another way that we could deal with motor noise is to try to minimize it from the start by avoiding movement solutions that have high noise. In the rest of the episode, I want to look at a paper that provides compelling evidence that we indeed do this. The paper I'm referring to is one published by Thorpe and colleagues in 2017. In it, they begin by pointing out that many motor control theories postulate that the central nervous system, or CNS, chooses movements that lead to low noise. These theories usually present the process by which we select movements as an optimization problem, in which a cost function consisting of noise, effort, or both is minimized through the choice of a movement. These models have been effective at predicting which movements subjects choose. However, prior to this current study, there was no direct evidence that the choice of movement solution minimizes noise because noise was not directly manipulated. To address this gap in the research, Thorpe and colleagues performed an experiment in which participants learned a novel perceptual motor task in which there was a redundant mapping between goals and movements. When learning to complete a task like this, users must form a control policy or learn a relationship between the endpoint movements and body movements. More specifically, in this study, 16 participants were asked to hold 2 inertial measurement units, or IMUs, one in each hand. Think of these as like Wii controllers. Participants were required to make small hand movements and were told that only the roll and pitch of the sensors was recorded. The roll and pitch of each sensor was linearly mapped to the 2-dimensional location of a cursor on a screen. This method creates a hand-to-cursor mapping in which a single position of the 2 hands results in a single cursor position, but a single cursor position could be achieved through multitude of hand positions. So in other words, there's redundancy in the movement solutions. Because the 2-dimensional location of the cursor was a linear combination of the 4 IMU measurements, roll and pitch for each hand, there was an infinite set of hand postures that could produce the same cursor location. For example, rotate the left hand more and the right hand less. To become proficient at this task, subjects thus need to learn the relation of their hand movement to the cursor movements. Participants completed 8 blocks, 4 per day for 2 consecutive days. Each block consisted of first training trials followed by testing trials. During the training trials, targets randomly appeared on the screen. Participants were instructed to move the cursor as quickly and accurately as possible to the target and maintain the cursor in the target location for 500 milliseconds. The cursor was always visible in these training trials. For the testing trials, participants made center outreaches to 4 target locations. The target locations in the testing trials were not experienced during the training. When participants left the center location, visual feedback was removed until the movement was completed. In other words, in the testing session, they measured transfer to a condition in which participants did not receive online visual feedback about their movements. Participants were divided into 2 groups of 8, the noise group and the control group. For participants in the noise group, artificial signal-dependent noise was added to the IMU measurements only during the training trials. For the control group, no additional noise was added during the entirety of the experiment. During the testing trial, no noise was added for either group. What was this noise? Well, it was actually based on some fairly complex mathematics that I will leave it to you to look at if you're interested. But there were 2 key features. First, the best way to think of the noise was as cursor jitter. So when participants' hands were completely still, the cursor still changed location slightly. This can be thought of as analogous to muscle tremor. The second key feature was that the magnitude of noise was posture dependent. So in other words, it was larger for some hand positions than others. For example, the cursor might jump around more when both wrists were bent forward than when they were straight. The idea here, of course, is that during learning, participants might avoid postures associated with large amounts of noise. The conditions were designed such that there was a single collection of hand postures, or a single control policy, that minimized cursor noise for every cursor location. This was considered to be the optimal control policy to which the actual movement solutions used by participants could be compared. What was found? Not surprisingly, adding the noise made the task more difficult, as on the final session, completion time, path length, and initial direction error were slightly higher for participants in the noise group as compared to the control group. However, this difference was not significant, so participants in both groups showed they could learn the task. But what about the key question? How does noise affect how the task is learned? Consistent with the prediction that participants would learn to use a movement solution that minimized noise, the actual movement patterns were significantly closer to the optimal ones for the noise group as compared to the control group. Finally, participants in the noise group performed significantly better in the testing phase with no visual feedback, suggesting that they developed a more adaptable, transferable movement solution. In sum, this study provides convincing evidence that participants learn to avoid movement dimensions that are responsible for task-specific noise. Quote from the paper, "Our results suggest that motor noise is an important factor that can guide how the CNS forms control policies, and that visual motor noise can thus be used as a tool to shape motor learning." End quote. So what are the practical implications of this study? As the authors suggest, one possibility is that this technique of adding noise to discourage certain movement solutions could be employed in rehab after things like stroke to help patients relearn coordination quicker. In terms of coaching, I think this idea that noise shapes motor learning is an important one to think about. For example, if as a coach you see that an athlete has difficulty maintaining a certain body posture or using a certain movement, in other words, there's a lot of noise present, you should be aware that they're unlikely to use these in developing their movement solution. If you think this is something that they really need to have, then it might be worth thinking of ways to reduce the motor noise in the system. For example, by addressing it through strength and conditioning. Okay, that's it for this month's bonus episode. Hope you enjoyed it. Thanks a million for supporting the podcast. I really do appreciate it. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled. As it flies, is this the way?